In this video, we're going to look at doing a transesterification reaction under basic conditions. So if we are doing a transesterification, what that means is that we are starting with one ester and we are wanting to convert this to a different ester. So essentially we are wanting to replace this portion of the ester. And so when that's kicked out in this reaction, that's going to form an alcohol. Right, and then we need to see, well, where is this new ester group going to come from? And so just like we saw with the acidic conditions, we want to use that as an alcohol. And we're going to use that in a large excess. So it's probably going to be the solvent. So it's often the solvent for the reaction. And if this is going to be under basic conditions, what we're going to do is we're also going to use this same group as a nucleophile. So we'd also use that as a nucleophile. Okay, so let's take a look at how this reaction is going to work. Let's look at a real example. And before we do that, let's just note that this isn't going to come by itself. It's probably going to be added as something like the sodium salt. So you'd probably see that as NaOR minus, and you'd want to recognize that that sodium is just a counter ion in this reaction. Okay, so let's take a look at a specific example and let's look at the mechanism. Okay, so let's say as an example that you were starting with methyl butanoate and you wanted to make the ethyl butanoate. So it's the identity of what you're adding that tells you what alcohol and what alkoxide you want to use. And since the methanol is being kicked off, that would be the byproduct alcohol that you would form. So we're going to take a look at what we're adding, and that's going to tell us, okay, we want to use a solution probably of sodium ethoxide in ethanol solvent. Okay, and so this mechanism, when we draw it, is a lot shorter than the acidic mechanism. It's a lot easier to draw. We don't have the proton transfer steps that we do when we do an acid catalyzed reaction. So that doesn't mean it's easier in practice. It just means that when we're drawing the mechanism and accounting for our electrons, it's faster to draw. Okay, so if you have sodium ethoxide in ethanol, what this means, we want to say what we really have in our solution. So in our solution, we have OCH2CH3 minus, and so this is available to act as a base or a nucleophile. And then we have the conjugate acid, the ethanol. And so this is the only acid we have in solution. So if we need to protonate anything, then we would use the ethanol. So it's always nice to know before we start a reaction what we have available to us to react. So our nucleophile is going to attack the carbonyl carbon. Under basic conditions, we can't protonate anything. We don't have a strong enough acid to protonate an oxygen. So the first thing that's going to happen is your nucleophile is going to attack the carbonyl. So we have our ethoxide nucleophile, and this can attack the carbonyl carbon and push those electrons up onto the oxygen. And so then we're going to have a negative charge on the oxygen. We have OCH3, and then we have, that came from the starting material, and we also have this new ethoxy group that we just added. Okay, and from this point, you might look at it and say, well, when this collapses, right, because this is going to come down and form a double bond, well, we might lose the methoxide and we might lose the ethoxide, and you would be absolutely right. Neither one of those is a better leaving group than the other, which is why we tend to use an excess of the solvent, so that we have an excess of just ethanol and ethoxide around to kind of drive this equilibrium towards the products. But when we draw our mechanism, we draw the steps that lead us towards products. So we are going to choose that methanol as a leaving group. So we'll see it leaves. And a lot shorter than the other mechanism. We've already got the ester product. And so we have formed methoxide as well. And if you want to explain how this becomes methanol, and you could still have some of it available as a methoxide, but you do have some ethanol around, and you could use that as an acid if you wanted to show where the proton is coming from here to form that methanol, right? And this ester is your target ester. And notice here you're also forming more ethoxides. Then you're generating more nucleophile that can go back through and react with more of that starting ester.